Okay, so we are going to see another examples that I mentioned earlier, which is also in the original paper by Fari. By the way, the paper by Fari contains so many more things that I will not tell today. It's a very, very rich paper. So it's called the ring of disagrees. And it's what I mentioned before already. So it's WACQT for graphs of degree 2. So then is what we, so the graph is the one that we saw. And we want to maximize the number of disagrees. So then we are going to color our vertices like this. The cost function is what we wrote before, but specialized to the case of now the edges are these ones, the graph is this, and each term is what we wrote before, minus sigma zj, sigma zk, plus 1. And you can see that the number of disagrees is n if the number of vertices is even, and n minus 1 if the number of vertices is odd. Then for each p, so we are going to do what we did before, to identify what are the subgraphs that contribute to the expectation value. But in this case, it's very easy, because as you can see, there is only one type of subgraph. For an edge jk, there is only this type of subgraph. Now we are focusing again on here p equal to 1. Otherwise, with p equal to 2, we could go even further. So then there are 4 vertices. And in general, for general p, then we can basically entangle more and more and more. And actually we can entangle for p 2p plus 2 vertices. And then what is the weight of this type of subgraph in the expectation value? It's n, because for each edge we get the same subgraph. So it's very simple in this case, since there is only one type of subgraph. Then basically what they do then, so basically fp of gamma beta becomes n times fg gamma beta, which is the expectation value on this subgraph. And then this they can evaluate numerically. And then they get the full, so they get the full thing for many p, because it's a simple calculation, so they can do it numerically. And for p equal to 3, 7 over 8, p equal to 4, 9 over 10, p equal to 5, 11 over 12, p equal to 6, 13 over 14. So then they conclude by inspection of this series of values for the expectation value of a subgraph, that this must be something like 2p. So they conclude that fg of gamma beta is 2p plus 1 over 2p plus 2. Then the final expectation value, the total one, is n times this. And this, you can see that when p tends to infinity, it tends to m. But in this case, n is also equal to m, because there are the number of clauses in this simple case is equal to the number of edges, which is equal to the number of vertices. So then we are really saturating the bound. And then they evaluate when p is equal to, so in these cases, they make the comparison of the approximation ratio with different p's. So what they get, so now define the approximation ratio as R over C max. So basically it's the ratio between the value that your cost function, once that you maximize this with the QAOA takes, divided by the maximum value, that in this case obviously is known, and it is M. So then they have for p equal to 1, okay, yeah, sorry. Okay, this, this is everything for the case of the ring of disagree, and then they comment on the 3 regular graphs that we saw before. Always max cut, so always the same problem. And they have that the approximation ratio that they get is 0.69 for p equal to 1, which is not as good as the classical one. I think the best algorithm for max cut is called Gauss-Williamson. But then for p equal to 2, it's better. Yeah, and then they also concluded that in principle it is not easy to know what is a good p for getting an approximation ratio that is best than what we have classically, and even if it was, then we wouldn't know if it's with respect to the best in absolute algorithm or what we have now. So this is the same thing that we were saying before. So this concludes the part on QAOA that is on the Fari paper about what I wanted to tell you. But this happened in 2014, so since then there have been a lot of extension and interesting results. So I wanted to finish with telling you what highlights of the research on QAOA in the past 5 years. And it's not exhaustive, so there is much more that happened that I will of course not have the time to tell about everything. But it's a very active field of research. Do you have questions on this? Yeah, let's go with the list of news. Okay, so first there is a paper by the same authors, that is archive 16.02.07.674, where they show that if you do this, you prepare QAOA state, gamma beta for p equal to 1 already, and it was again for WACQT. And then now you do measurements in the computational basis many times. So these samples could not be efficiently sampled by a classical computer. It means that it is hard to sample, computationally hard to sample for a classical computer out of the probability distribution that correspond to this state already for p equal to 1. So this is a hint that the quantum computer is preparing something. So it's the same thing as the random quantum circuit by Google, for instance, with a very small depth of the circuit. And also we will see next week, we will have a lecture on this kind of sampling models. But it doesn't mean that for p equal to 1, they are solving the problem that the classical computer cannot solve. So it doesn't imply anything about the comparison of the performance for the problem that you are trying to solve. It's only about the sampling. So QAOA, sampling from gamma beta is computationally hard. And in particular, it is not in BPP, which is bounded probabilistic polynomial time. So it's what a classical computer can solve in polynomial time with a random number generator. So this is your laptop, your MacBook. And also here they also show that it's not in fast BPP, which instead is a super big class. And then they compare with quantum annealing for the same problem, which instead is in post BPP with stochastic Hamiltonian. But it's not, it doesn't mean much actually, because this is also, so this is still a super big class, is not BPP. It's BPP with post-selection, so it's a super big class. So it doesn't mean that this quantum annealing with stochastic Hamiltonian is not doing something that a classical computer could do. So it means that we don't know, basically. But this QAOA seems to be more powerful in this sense. Yeah, this is probably not very talkative as a result. Then there was a lot of generalizations, and in particular, one thing that was called, so this is, let's say, quantum supremacy. With QAOA. I would say this is the most important part of the result. Then there was a generalization where QAOA now stands for quantum alternating operator ansatz. And it's a generalization of QAOA. One of the authors is Eleanor Rieffer. I mentioned her because she came to Gothenburg in our WACQT summer school a couple of months ago. And the reference is this one. And then here, instead of using the operators that I mentioned before, for alternating, they alternate a sequence of operators that are more general. So this is a general family of operators that depends on the cost function. And then now the mixer, it's a family of mixing operator that depends on the structure that you have. And in particular, it is used, if you have a constrained problem, it is used to keep the evolution in the subspace that satisfies the constraint. So then in the same line, there is another paper by Farid and collaborator, where it's a little bit in the same flavor, a generalization of the original QAOA paper, that is called then native architectures. And then this is interesting because it's also about, so you suppose that, I don't know if I mentioned it explicitly before, but we have seen QAOA where the operator that depends on the cost function is really depending on the cost function with the connectivity of the problem, which might be very, very difficult to implement in the lab. Even if we saw only here like a 3 regular graph example of WACQT, but if instead you have an all-to-all connected problem, then you have to use, implement an evolution with an operator that is all-to-all connected. Is a mess. So this paper tells you, if in the lab you have a different connectivity, you have a grid, for instance, you can still run QAOA with your grid Hamiltonian and the standard mixing one, say. And then the only thing is that you make a distinction between the Hamiltonian that you use for the evolution. You know, we have seen this gamma U, gamma C, and then you have the U, B, okay, this should be here, U, beta, B, which is the mixer. So this one, you use for this evolution the one that you have in the lab. Then you get a string, and then you evaluate the cost function that corresponds to the Hamiltonian of the problem. So you separate the role of the Hamiltonian. Here it's in the original QAA is the same. The same Hamiltonian has the double role. It has the role of making the evolution in the lab to prepare the quantum state, and then you evaluate the cost function, and then you do the classical optimization. Here you separate the two things. You use the Hamiltonian that you have in the lab to do the evolution, but you do the classical optimization evaluating the cost function of the true problem that you want to solve. And then what they show is that they still get decent approximation ratios that are in between. Before I wrote the two numbers at the board for p equal 1 and p equal to 2, and they get, and I forgot to write the classical one, but it was in between the two. And they also get something here that is in between the two. So it's in between what the quantum with the true Hamiltonian could do and the classical one, say. It's not too bad. And this is archive. And then they mention also a second result here that is about opening up the parameter space. You have seen that here in the original QAOA, so in this sense it's a bit similar to this. It's about considering broader classes of Hamiltonian for the evolution than the original one. So one is this, one result is this, and the second result is about using, for instance, different angles for your rotation. Like you would have a sigma I, sigma xi. So you would allow your single qubit rotation to have a different angle depending on the qubit. So this means a lot more of parameters to optimize, maybe too many, But what they say is, so it will become like very non-efficient, but maybe they argue that it could also, depending on the problem, to get a good numerical approximated solution. Very, very heuristic, but why not? It's a possibility that I mentioned. And then a very interesting paper also by Fari, and it's about for the Sherrington Kirkpatrick problem, which is basically nothing else than this Hamiltonian. JK. I don't remember now how they choose the JK, if it is antiferromagnetic. I don't remember this, but the point is that the crucial point of this paper is that for this, in the limit of infinite size, they are able to compute analytically, even analytically, the optimal angles. And then similarly, there is also, so this one is archive 1910 08187. And then similarly to this result connected, there is another paper where they are able to evaluate analytically the optimal angle for spin glass problems where you have random instances. They show that the optimal angle for different instances of how you chose the coupling, how you chose the problem, they concentrate. So basically that in the limit of infinite size of your spin glass, you can extract randomly this Jij, and then the optimal angles are more or less always the same. They concentrate statistically. What they don't know out of that, if those optimal angles would even work for the hard instances of the problem, which are the ones of interest. This they cannot say. But then it's about, again, calculating gamma beta analytically for spin glass. And this is live strife, and it's archive 1908 08862. And then I also wanted to mention that there are a number of people that have been comparing the performances of QAA and quantum annealing for specific problems, and the results depend on the problem. There is a paper by one of our OpenSuperQ collaborators, that's why I mentioned this one, where they consider TOSAT and also MaxCut for unweighted graph. So basically where the coupling can take a different value depending on J of the edge. And then this is by then Christian Mikkelsen. And collaborators, and it's archive 1907, and it's QAOA versus quantum annealing, and here for this problem they are much in favor of quantum annealing actually for all the instances that they examine. And it's a very, very active field of research. There are also activities here at Chalmers in the group of Andreas, has been doing experiments in our theory group, so hopefully soon there will be more papers to add to the list. And yeah, it's a very active field of research. The people must especially characterize the performances. So you are very welcome to contribute to this in the forthcoming years. And yeah, I think I told you everything that I wanted to tell you.
Do you know why many of these papers are only on the archive and not the journals?
Of the list, the only one that is published is this one. But because it's recent, this
Yeah.
is because it's recent. Then Fari is so established that he doesn't bother anymore in submitting papers for review.
I also think like there's the Seth Lloyd paper on that QAOA
Is universal.
Yeah, that's also only on the
Yeah.
archive, I think. And
Yeah, those kind of people, I don't know what is the philosophy for them. You know, the editorial publishing scientific system has a lot of flaws.
Sure.
We will produce work unpaid, the reviewers are unpaid, and as a consequence of this unpaid work, somebody gets money. And we have to pay to access what the other people did. So there are people who are doing some activism against this, and they only have open access. The bad part is that in science, it's even if the quality of peer reviews have become dramatically down, because we are the system doesn't, how to say, glorify, like it doesn't give anything if you are a very good reviewer or not much. You get publon, but nobody knows the publon, what they are good for. But still it's good, the process of having some peer to take a look to your results, but it's a very complicated thing. I don't know, I cannot give better answers.
I just feel like especially for QAOAs, but there's a lot of unpublished, so to say, papers.
Because a lot are from Fari,
Yeah, maybe. Yeah.
and he doesn't submit, and Lloyd, yeah, also.
Or even like the experimental one, like from WACQT, for example, it's also on the archive since 3 years or something.
One other reason, yeah, I know which one. I didn't mention, but it's also in the list. But I could also add the reference. But also there was one by Aspuro Gudzik on using QAOA for factoring. That was also on archive. Also one other reason is that it's very new and we don't know to which journal to submit often. But yeah, I don't know. Okay, then we can stop it here.